All right, thank you so much for being here for our very first session with the Gemini South team. My name is Jamika Marshall, and I'm very pleased to serve as the Shadow the Scientist Programs Manager. The Shadow the Scientist initiative is brought to you by a fabulous team at the University of California, Santa Cruz. Now, as I said, I am very thrilled to host our very first session with the team from Gemini South. We have the privilege of shadowing Lindsay McGill and Roque Ruiz, who are now in the control room located in La Serena in Chile. Now, the International Gemini Observatory actually consists of twin 8.1 meter optical infrared telescopes located on two of the best observing sites on the planet. Now, today, the Gemini South telescope, which we're featuring, is located on a mountain in the Chilean Andes called Cerro Pachón, with a very dry and negligible cloud cover make this another prime telescope location in the Southern Hemisphere. Both of the Gemini telescopes have been designed to excel in a wide variety of optical and infrared capabilities. By incorporating technologies such as laser guide star adaptive optics and multi-object spectroscopy, astronomers in the Gemini partnership are able to explore the universe in unprecedented depth and detail. I am very, very pleased that we have a stellar team of science hosts tonight, and that includes members of the Gemini North science team, who are located in the Hilo base facility, which is where I am. And we are also joined by members of the NASA Speckle imaging team. This is a thrilling session with lots of amazing experts. So let's get started with members of the Gemini North team. Maybe with Brian Lamone. We have Emily Peavy. Brian, Emily, aloha.
Aloha.
Aloha, Jamika.
All right. I see you all there in the conference room. We're used to seeing you in the control room when we are doing a Gemini North session, but this session is super, super special. So I'm thrilled that y'all can get us started and tell us all about what's happening.
Oh, yeah.
Yeah, sounds good. So for those of you who don't know me, I'm Brian Lamo. I'm a staff scientist here at Gemini North. And what that means is I help with the observations both in the north and the south. So I support programs both in the north and the south. I observe on the telescope here in the north. Just for context, it's 3 p.m., 3 o'clock in the afternoon here in Hawaii. So we are not on sky, but we have two telescopes. One here on Mauna Kea on the Big Island of Hawaii, and then one in Cerro Pachón, as Jamika already introduced. And in Chile right now, it's 22:08, and the sun is set. I think the sun set about an hour and 10 minutes ago, or 20 minutes ago, something like that. So they are actually on sky, and so Lindsay and Roque are they're observing right now. So we have a 7-hour difference right now, and in about 3 hours, we will go on sky. Hopefully, it's kind of cloudy here, and we'll start taking our observations. So this is a thrill for me actually, because I've only shadowed the Gemini South team a couple times. It was actually Roque, I think, that called me first for a program that I was observing on Gemini South that he was observing for me. So we're thrilled to join them and to be here. And Emily's in the room with me.
Yeah.
Emily.
Aloha, everyone. I'm Emily Peavy. I'm the Senior Education Engagement Assistant here at Gemini Observatory. I always love helping out with the scientist sessions in order to really see and witness some of the amazing things that are happening and seeing how that data is coming in. My specialty is answering questions and trying to find ways in order to bring science down to earth sort of thing. So I'll
That
be
all of our specialties.
yes.
Great questions.
Oh yeah, that's very
Well, asking
true.
questions and answering
Asking
questions.
questions and problem solving. I
Sometimes-
always say that
sometimes
everyone's a
answering
problem solver. Yeah, oh, and finding questions too.
And then more questions after you get those answers.
That's how science works. It's just question, question, question. So I'll be helping out in the chat with any questions that anybody has throughout the session.
Yeah, and that's a great point. Please, anybody, this is totally organic, so please interrupt us at any time. You can raise your hand, I think. Also, you can ask questions in the chat. So we're more than happy to answer any questions as we go along.
Yes, so everyone can raise their hand, and questions, comments in the chat will come to co-host only, or to me as the host and to co-host only. So I will share them with the larger group. All right, and welcome. I see we have a few more people who've joined us. I'd like to welcome you all. Daniel, Ferry, Jennifer, Josh, Luis, Rob. So glad to have you in our virtual session today. If you have any questions, as I said, just let us know. We just started with an introduction from our Gemini North science hosts, Dr. Brian Lemo and Emily Peavy of the Communications, Education, and Engagement team. And we have some other science hosts with us from the NASA Speckle team. Zach, welcome.
Hey. Hey, so my name is Zach. I am a former Gemini Science Fellow and now working at NASA Ames with the NASA Speckle team as a NASA postdoc. And yeah, I'm happy to be here.
Wonderful. Thank you so much, Zach. And for those of you who are just joining, I'm sure you know this is our very first session with the Gemini South team, and that is Lindsay and Roque. They're in the control room in La Serena. Now, Zach, we were originally going to be having some speckle imaging action happening tonight, but as happens sometime when the universe gives you lots of amazing things happening at once, things change. So what's happening?
Or when it comes to the end of the semester. We have RTOs, rapid target of opportunity. This particular program was awarded time for events that occur suddenly, so supernovae, gamma ray bursts, etc. And so this program triggered. They said we want to take an observation, and they were particularly awarded a rapid trigger. So that means that pretty much within 24 hours, we're supposed to turn around and give them the data or observe the target and make the data available to them. So that is what is happening right now. And so that means we put speckle observations on hold. So actually the people who are the team members who are supposed to be observing the speckle night are actually not here right now. They are waiting until it is time, which will be in like an hour or two. So yeah.
Yes,
Fun
it's about
time.
another hour 15 until this target is gone.
Half.
Is that the plan? So likely we'll get to see some speckle imaging, given that it seems pretty nice conditions down at Cerro Pachón, that we might see some speckle imaging by the end of the session.
Yep.
So our assessment.
I love it. So now these rapid targets of opportunity, why do they replace what was already going to be happening? Is it that clearly they have a priority? Is it because these are spectacular, one of a kind events that are happening in the universe, or is there some other reason why they get priority?
Zach, I could take this as a QC, as an acting QC right now.
Oh, yes.
Yeah, so So for those of you who aren't familiar with the model of how we operate as an observatory, so again, we have 2 telescopes, which means that we can see the entire sky, at least when it's nighttime. So we can cover the entire celestial sphere. And we have a lot of different types of observing. So we have observing with multiple different instruments on a given night. So we have our 2 telescopes, which are our light buckets, and then those type 2 instruments where we can either use the instruments as imagers, so just take pictures. We can use imagers to disperse the light, so make a rainbow, make a spectrum, and measure distances to objects, or chemical abundances, or the amount of dust in an object, or whether dust or how many stars it's forming, so on and so forth. We have speckle imagers, so we have identical speckle imagers on the 2 near identical speckle imagers on the 2 telescopes. So the one in the north, which we featured in another Shadow of the Scientist session, is called Alopeke, and that's the Hawaiian word for fox, and then Zorro, which is the Spanish word for south. So tonight's observations, we actually block out. This is fairly rare for the observatory. We block out a set of nights that are more or less dedicated to that instrument. So Alopeke and Zorro are visiting instruments. We have facility instruments and visiting instruments. They're visiting instruments because they are kind of loaned to us in partnership with the NASA Speckle team. And as Zach mentioned, there's the NASA Speckle team comes on and they help with the observations. So they help Lindsay and Roque, who are observing tonight, manage which targets to go to and for how long to spend on those targets. But normally we're in a queue system. So we normally do observations where we have a pool of observations on a given night. And even for Alopeke or Zorro, they have a pool of observations on a given night. And so they extract, based on the conditions, the observations that they think will bring the best science. So that's our job as an observatory, to get the best science out of every second that we're open. And so there's a person who right now in the north is me, but luckily I only have to do this for a week and then I shift off to another person that decides which science observations might be best for a given set of weather conditions. And at any given night, if I'm the queue coordinator, have to make about 10 different plans because we don't know the weather a priori. So we don't know whether it's going to be clear, whether there's going to be turbulence on the ground, whether even like one of our instruments may not work. And so we may have to take that into account. In fact, I think Lindsay, your guys' F2 is not working this evening.
F2 is, as far as I know, working tonight.
Okay.
But at the end of last night, we had a problem where the Zorro software crashed and we couldn't recover it. And then we had to switch back to Q, and we did GMOS, I think it was, for the last
Okay.
hour
Sorry, I
and
was
a
just
half
looking
or
at
so
your
of the
visit
night.
status page, and it says F2 is not available for observations, and it was valid until the 14th.
Let me double check and fix that if we're having a problem. I know we've been
Okay.
having some issues with the not always updating, right?
Okay, sounds good.
So
Yeah,
let's
so
see.
as Lindsay mentioned, one of the instruments, Flamingos 2 is the name of the instrument, was not working yesterday. And so a queue coordinator has to take that into account, because on any given night, we have observations from 3-4 different instruments that are available. And so we can choose between those, but it may be that at some point during the night or in the afternoon, an instrument goes down, and then you have to shift the observations such that you can still get the most science out of every second that you're open. And so these are kind of our regular planned observations. Like on a given night, I make a plan, but astrophysics is full of things that wreck your plans. Which is one really fun part of the job, is that it's humbling and humiliating all the time. And so we have these special programs. So a set of scientists fly to the observatory and they say, hey, listen, observatory, I have a wonderful idea. There's these objects called gamma ray bursts. and they can come from collapse of massive stars, or they can come from two neutron stars running into one another, or a variety of different other things. And I think these are super interesting. I don't know very much about them, and we as a community don't know very much about them because you need to observe them like right after they happen. So something goes bang in the universe, and a telescope that is not our telescope surveys the sky every day or 12 hours. And it says, wait, oh, something just happened over there. Something bright just flashed that wasn't there before. And then this team gets that data and they say, oh, yeah, you know what? That might actually be interesting. And so we have this latent pool of observations, if their program is accepted, this latent pool of observations that they can say, hey, yes, something just super exciting just happened. I want to take a better look at that. And we, being the telescopes that Gemini has available, being some of the biggest in the world in optical near infrared, we can take a pretty close look at these objects. And so they can do what's called interrupt the queue, and they can do it in a rapid way. So this is what Zach mentioned. So rapid target of opportunity. This is where we're by kind of contract, scientific contract, we're obligated to give them the data in 24 hours, if at all possible. So the science team can say, I want the data like right now, like please stop whatever it is that you're doing and slew to this observation. So they have that ability. They just need to like let us know that. Or they can say, you know what, a couple hours from now is fine. I don't want to like destruct, what you guys are doing, but please do it in a couple hours. Or they can say, no, 24 hours is fine. We also have what's called a standard target of opportunity, which the typical cadence for that is like a week. So it's just sometime in the next week, please get this observation. And so we have these two categories for this type of program. And typically we have, well, I don't know, 7 or 8 of these programs sitting in our pool of observations at all times. And any one of these scientific teams can press a button. Basically, they literally just press a button, and we get alerted. And it'll all of our computers will start flashing, and it'll say, "Attention, target of opportunity." And if you have the sound turned on, and so then if you're a Q coordinator, then your stomach drops because that means that all of your carefully laid plans have gone to waste, and you have to redo everything. But if it's after 5 p.m. here in Hawaii, then you're out the door, you're at the beach, and it's the lucky observer that gets to do the moving around of all the observations. So we had a trigger, actually we had 2 triggers here in the north today. So those are observations that I had to deal with. It could very well happen that we are triggered again on the north, and I will have to go run and do some work before 5 p.m. And the plan was to do speckle imaging, I think, all night tonight. But during the day, the Chilean day, Gemini South was triggered on, and Zach actually let us know that, because then the speckle team is alerted and said, hey, is it okay if we interrupt? Or no, by contract, we have to interrupt. And then people maneuver around. But it's usually very collegial in the sense that everybody wants the best science. And unless somebody like absolutely needs to get on sky that instant, there'll be flexible. The team will say, do what's best for the observatory, but we would really like it in an hour or 2 if at all possible. So I guess this target was setting. It's like an early evening target. And so it was really important to get to it basically as soon as the sun set. And this is one of those targets that probably getting on it as soon as possible is the faster you get on it, the more scientifically interesting it is.
It's great to see how everything works together, though, because we don't normally get to experience this during one of the live sessions. We maybe heard about it happen beforehand, or maybe it has to be observed, later. But now for this session, it's happening, and it's changed things around. So it makes it a bit exciting, although kind of crazy for the QC. So sorry about that.
If we weren't crazy already, we wouldn't be in this job. That's for sure.
Zach, can you tell us a little bit about speckle imaging?
Yeah, so the basic premise behind speckle imaging is we want to really resolve things that we can't resolve in seeing limited images. So when you take a long image with a telescope, let's say with one of our other instruments, GMOS, Flamingos 2, uh, what happens is you're staring through an atmosphere, and that atmosphere will limit the amount of resolution you get. So when we say seeing limited, it's what the atmosphere is giving you. So, you may hear people throwing around, we're at a seeing of 1 arc second or a seeing of 0.6 arc seconds or zero point 0.7. And that indicates that we can resolve objects separately down to that limit. And with speckle imaging and speckle imaging is a form of diffraction limited imaging. We want to get down to the diffraction limit of the telescope. So each piece of glass, each mirror that we have around the world has a diffraction limit down to some set value of arc seconds or angular what unit, whatever. So for Gemini, for example, at about in the optical at about red light, it's about uh 25 milliarc seconds. So that's very, very small. Um and is but in order to get down to that, we have to use special techniques to reach that limit because normally there's this pesky atmosphere in the way. And so the two main ways that people do it are through adaptive optic systems and speckle imaging. So both of our telescopes, Gemini South and Gemini North, have adaptive optic systems. Gemini North is called Altair, Gemini South is GEMS, and what those allow you to do is there's basically little deformable mirrors in the instrumentation that allow you to take out the aberrations from the atmosphere on sky as you're taking the data. And so you're taking this data, you have to correct on sky, you have to have bright guide stars in order to correct the atmosphere or a laser. And you do this on sky while you're observing the target so that you get diffraction limited images that way. Speckle imaging, on the other hand, is where you basically take you take really, really, really quick images. So when we take images with Alopeke and Zorro, we're taking data with frames that are about 60 milliseconds. And we take 1,000 of those in what we call a data cube, and we take multiple data cubes per target. And by going this fast, what happens is we're able to freeze the atmosphere in each frame. And so then you're able afterwards, after you have all this data, you can go back and using a bunch of different equations, mainly Fourier analysis, you're able to reconstruct the image that you're seeing without the atmosphere and get to the diffraction limit of the telescope. And so this is really good for what we really want with speckle imaging, which is resolving nearby stars to other stars. And so a big part of the speckle team's project, and the reason it exists, is to support NASA exoplanet and community exoplanet missions. And so in particular, what it's really good for is looking, or what is its main goal is to go look at tests, targets of opportunities, or tests, TOIs is what we call targets of interest. And these are systems where TESS is another space telescope that's currently floating around that stares at portions of the skies for 30 days and gets light curves on all the stars in that area. And then what people do is they go and look at these light curves and they see little tiny dips for the planets passing in front of them. And those are what we call targets of interest, where there's a potential planet detection. And the reason you want to know whether there's another star in that around or nearby that system is because if you have two stars together and I guess I'll preface this by saying that the test pixels are very, very large on the cameras. They're very large compared to other things, compared to other astronomical things. They're about 27 arc seconds across. And compare that with, say, what we were talking about with Alopeke and Zorro, where we're getting down to, milli-arc seconds in resolution. 27 arc seconds is much, much bigger than that. And that's the size of 1 pixel. And so within those 27 arc seconds, you could have multiple stars landing on that pixel. And so you need to figure out where the light from your exoplanet host, potential exoplanet host, is coming from. And if you have another star in that bin of light, then what it does is it adds more light into your system that isn't associated with your star. And what that does then is it throws off our estimates about the planet parameters, because a lot of the planet parameters that we get from the test light curves, they're all taken from basically what do we know about the star, and taking that information and building it into models for the planet. And so if our information about the star is wrong, then our information about the planet is also going to be wrong. And so ultimately, at the end of the day, our goal is to find those nearby close companions that you may not see when you stare at the star with just GMOS imaging here at Gemini. But if you use speckle imaging, or if you were to use adaptive optics, you would see 2 stars instead of 1. And so that would allow us to reevaluate what we know about an exoplanet around those 2 stars. So that's the long explanation. So if you have any questions about it, because I'm sure I was confusing as all heck. So
I was really understandable. I now finally understand speckle imaging after 4 years of talking to you.
You would always talk about speckle imaging, and you'd be so excited and thrilled about it. So it is amazing to see that now you're focused on that, and to have you back on as an expert to talk to us about it is really thrilling, Zach. And yes, we do have a question. So Rob asks, can you explain the difference between speckle imaging and stacking? What's the difference?
if by stacking what you mean is shifting and adding, the difference is that shifting and adding, for the most part, you're not doing any additional analysis on it. You're taking the images, you're shifting them together so that the bright pixels are on top of each other, and adding them together to form an image. There's another type of I wouldn't say speckle imaging, but really diffraction limited imaging, called lucky imaging, where you also take a bunch of short exposures. And in that, what you do is you go through and you basically have some measure for each frame about how good the seeing is in those frames. And maybe 1 or 2 of those images are really, really good seeing, and those are your best quality. With speckle imaging, what we're doing is we're taking all of the frames that we have, and we're basically converting them into frequencies to pick out any companions that we see. So we're doing what we're called Fourier transforms on all of these speckle images, um, and basically creating the power spectrum of these images to see uh, what frequencies we see. Because what's happening is when you have 2 stars, and you have 2 stars shining down through the atmosphere is going to disperse that light and have it interfere with each other. And so this interference.
You like when we did the Alopeke session, you had a nice animation, I think.
Yeah, that's
Not
what I
that
was just thinking of.
It would be awesome to see it, because it is actually pretty neat to
Let's see
watch.
here. Yeah, I was looking through.
And we'll see it
my
like
thoughts
when the Zorro observations are taken. I mean, you can see the speckle that's flickering
Let's see
all
here.
the time.
Where the heck did I put this talk? I think it's in Google Slides. I think that's where it is. Yeah. Is it here? Nope. Lovely. Is it here?
Sorry if I interrupted your role, but I really like that.
Oh my goodness.
And I was going to ask Brian, so thank you for doing that, because I have some images in my mind of what it was like, but it's been a while since we talked about speckle imaging. So this is perfect. And while Zach is doing that,
I got it.
Oh, you got it?
Go ahead. Go ahead.
Ooh, no. Go ahead. It was a filler. You're on.
So, all right. Can I share screen?
You should.
So this is kind of the field of view of what Alopeke and Zorro see. That's a 256 by 256 pixel grid. This is about, I think it's like 2 or 3 arc seconds on the sky is the field of view here. And so as I press play and we go through time, you can see that you can see the star is jumping around. This is a star taken at 60 millisecond frames. And so you can see it's kind of jumping around, and that's because of the atmosphere. And so what we do is we take all of these frames, all the frames that we take, and we normally take for, let's say, a 10th magnitude star in V, we normally take about 5 to 10 frames on that. And so that's about 5,000 to 10,000 frames in total that we put into a reduction. And then what we do with that reduction is we use Fourier transforms and move it
So
into.
Zach, sorry, so you take 4,000 to 5,000 frames over what period of time?
So 4,000 to 5,000 frames, 1,000 frames is at 60 milliseconds is a minute, so that's 5 to 10 minutes of on sky time.
Okay, all right, so super fast.
Yep. And then what we do is we take all those frames, put them through this Fourier analysis, and at the end of this, what we get is this image here. And this is where we've effectively reconstructed what we see on the night sky. And so in the middle here, you see our star. And and this is just with a couple of frames. And if you start to add more and more of these frames into the analysis, what happens is you build up the signal, and you build up the signal, especially in any companions in the region, and you get a companion to pop out of your data. So that is the terrible explanation that I have for for it. Because it is a lot of math. There's a lot of Fourier transforms, and I have yet to settle on the best way to explain it. But
so Zach, why don't you use like Hubble or James Webb? I mean, those are in outer space. Why don't you use that? Because then you don't have to deal with the atmosphere.
you're right. But we can't put 8-meter pieces of glass into space right now, at least as cheaply as what we have on the ground. And so, with Alopeke and Zorro and Hubble in particular, Hubble's resolution is about 40 milliarc seconds. You could probably push it a little bit more depending on the filter you use, and depending on your reconstruction algorithms. But with Gemini and Alopeke and Zorro, we beat Hubble in angular resolution just because we have an 8-meter piece of glass versus a 4 or versus a 2.4. And so that's the particular reason why you want to go here. Now, the great thing about Hubble, and a lot of people have done this, is that it can go a lot deeper in the area in the surrounding area around the star where it can see. So I think Hubble's limiting mag is like 20th, 25, something like that. And they would be able to get that deep on a target relatively quickly, that they can see. And comparatively with Gemini and Alopeke and Zorro, we're getting delta magnitudes. The difference between a companion star and the host star of about 5. So Hubble can go deeper in terms of companion magnitude, and that's also something that adaptive optics can do as well. Another reason is that Hubble time is very hard, very, very, very hard to get, and Gemini time is very, very hard to get. There's a different amount of varies there. So
I was counting the amount of varies. Was very, 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 very.
Yeah,
It's
so
also
Hubble and James Webb, it's somewhere around 5 to 10% of the people that apply get time. Gemini depends on which partner country you apply from, because we have 6 different partner countries, but around 20% success ratio. So that's the difference between 3 varies and 2 varies.
And another thing that is, as these telescopes in space are getting older, although James Webb is very new, there is the concern about fuel. And a lot of with a lot of the people who use speckle imaging, we're looking at bright targets, and we go through a lot of them in a night. On a good Alopeke and Zorro night, we're probably going through 100-ish targets. I know at SOAR, which is another telescope in Chile, on Cerro Tololo, or not on Cerro Tololo, on Cerro Pachón. It's right down the road from Gemini South. There's a speckle imager there that goes through. I think the max they've gotten is like 300, 400 targets in a night. So, and if you're wanting to use Hubble for that, that takes a lot of fuel, a lot of slewing fuel to do that. So it's kind of like it's not a great use of resources in that regard.
We move pretty fast here on the ground. We can slew from one side of the sky to the other side of the sky. Actually, and a lot of times you guys are looking at transit stuff, right? So it's not even, you're not even slewing from one side of the sky to the other side of the sky, but we can do that in a couple minutes, no problem. And it takes James Webb or Hubble much longer than that. And then I guess there's the cost aspect too. So like James Webb, I think it was like around 10 billion to build and continually operate. And Gemini is like in the 200 million-ish category. So you could build 50 Geminis for one James Webb. So you could do a whole lot more speckling if you wanted to. We could have 48 more on the ground speckling.
I mean, one of the big things coming in at least in my opinion for space is the Roman Space Telescope is going to be launching, and a big thing with speckle imaging and the work that I'm doing, which is finding close companions, is big surveys are a huge plus for it. So Gaia survey was huge for us. Roman's going to have a big survey where their goal may not be to find companion stars, but they're going to take the images anyways, and we can go steal those images and find the binaries that they don't really care about. So it is definitely cheaper and less logistically challenging to do it from the ground, but there are instances where space does a lot for binary astronomy.
Yeah, so synergistic, I think, in the end, right?
Yeah.
So while we aren't able to to get into speckle imaging just yet to see to really see what Zach was talking about, I think maybe we can see what's going on right now at Gemini South with Lindsay and Roque. Brian, what are we looking at?
Yeah, right with you, Jamaica. So so Gemini North and Gemini South are sister telescopes, not identical twins for sure. This is actually my first look at all of the software infrastructure of Gemini South. So this is the first time that I've been able to fully eavesdrop on their observations. We just got this up and running earlier today, actually. And so we have some software that's identical and some software that's a little bit different. So we can just kind of random walk around here, and I can say some things that I know, and maybe I can defer to Lindsay if there's something that I have no idea about. But so this thing on the left here is identical effectively to what we have in the north. And this is we have tons of acronyms. In fact, we have a page that we have to go on that tells us what acronyms are what, because we have 8 screens open here in the north, 6 in the south, and both the observer and operator. Lindsay's the observer tonight. Okay, is the operator. Each one of them has these 6 different screens, each with a different set of software. So to talk about it quickly, we usually use acronyms. So this is the TSD, or telescope status display. And so there's a huge amount of information on this. But what this is basically is a rendering of the telescope and the subsystems of the Gemini South telescope. And so on the left here, can you guys see my cursor?
Yes.
Hard, but
Yeah.
we can see it.
Yeah. Yeah. Oh, I see it over there. Okay. So yeah, so this is the rendering of the dome structure. This is where so this circle right here is where the telescope is pointing. This is the shutter. So this is this big set of doors that open up at the top of the telescope structure to let in only the light that you want, pretty much. And then cardinal directions and the directionality of the wind. So you can see that they're pointed not directly straight up, which would be here. They're really down on the telescope structure here in this rendering. And you can see this number right here, EL, this is the elevation. So they're pointing at roughly 45 degrees. So this is halfway between straight up in the sky and the horizon, which would be 0 degrees. So 90 and 0 degrees. So about 45 degrees. There's also this other number, AZ, which astronomy stands for azimuth. This is degrees east of north. So they're pointing 268 degrees east of north. And then we have a ton of other information on here about the instruments that we're using on a given night, about our wavefront sensors, various measurements of focus and other measurements of interest as we're trying to get the most light into this small pupil for the instrument. There's this measurement of seeing here, which is something I think Zach mentioned earlier, which is basically a measurement of the turbulence of the atmosphere and the combined turbulence of the atmosphere and turbulence on the ground. So basically, if you take a point source in the sky, you just shine a flashlight down with a really, really, really tight beam, and you shine that through the atmosphere, it's going to start to speckle, like Zach showed. There's going to also be ground layer turbulence from heat waves, a variety of other things. And so this is all going to combine to scatter out the light. And so something just happened where the on-instrument wavefront sensor is measuring a very large value for seeing. So 5 or 4.78 would be near unheard of, although I've seen this on Mauna Kea before. But that was probably just a blip where there was a mismeasurement or they were not guiding. And so now it settled back down to a level that's fairly normal. Like less than 1 arc second is very typical in Cerro Pachón or in Mauna Kea, and in fact, really less than 1 arc second. 1 arc second is so arc second is not a unit of time; it's a unit of angular measure, and this is 1/3600th of a degree. So a degree is roughly 2 full moons together. So this is 1/1800th of a, doing math right, 1/1800th of a full moon. If it's the other way around. Anyway, so very, very small angular measure. And so this is how this is the resolution at which you're able to separate out 2 objects. And so the types of, like, I don't know what was the separation of the 2 objects that you showed us, Zach? Less than 0.2, 0.3, something like that.
Yeah, it was probably like 0.1, 0.2.
So our ability naturally under natural seeing conditions, which I think Zach mentioned that term earlier, under natural seeing, best we ever do, if we're observing in like the mid-infrared, we have a nice night, we could get down to conceivably 0.2 natural seeing. So I've seen that before in the L band or M band, which is like a 5 microns. But it's pretty rare. And in the optical, this measurement is done in the V band. This is the parenthetical statement there. So V, which is visual, stands for visual. So this is basically right where the sun peaks in terms of its output. So the wavelength wavelength of light that it outputs the most. And so this is, yellow-ish. And much more typical value of seeing is like 0.6 or 0.7. And so it would basically be impossible to get down natural seeing to below 0.3. I've seen roughly around 0.35, 0.3 at best ever. And so we would never be able to see naturally what Zach and the NASA Speckle team can see with this incredible technique they use. So yeah, this is something that both the operator and observer keep an eye on. At nighttime, it's just an basically orientation. There's all sorts of important data on here. When things start flashing yellow or red, this is when start to pay attention to it. Luckily, it generally doesn't do that. On the middle here, this is a side view of a rendering of the telescope where the light is coming in from the astronomical source. It's hitting the primary mirror here, reflecting up to the secondary, then being piped. There's literally a pipe in the primary mirror, and the light moves into the tertiary mirror, which is down here. This is called the science fold. We use this for our instrumentation cage. So so we have 3 instruments, I guess, on tonight plus Zorro. And so if it's piped to GSAOI, the light would just go straight through, and this tertiary mirror would be removed. Right now, the instrument that's being used is the Gemini multi-object spectrograph South. So this is whether the light is being reflected to this GMOS. It's not genetically modified organisms, but rather our workhorse optical instrument, both in the north and the south. So we have 2 instruments which are basically mirrored. The first is Alopeke and Zorro, and the second is GMOS North and South. They're not exactly identical, but they're fairly close. And so this allows us to take images in different colors. It allows us to take slit spectra of a single source, which is, I think, what is happening right now. Multi-object spectrographs, so you can take up to, well, actually, if you design your masks well enough, you can take up to 600 objects at a time. You have to be really clever in the way that you do it, but more typically something like 50 objects at a time. So if you have 50 objects in the sky that you're interested in, usually you take an image and you say, oh, I like those. I'm going to put a slit on those, and I'm going to only collect the light from those galaxies and then or objects, and I'm going to disperse the light, and then I'm going to look at my detector, and I'm going to try to figure out some information about those objects. And so that's a mode. That's the MOS part of GMOS. And then we also have integral field unit capabilities, which is basically that you can take a picture of the sky, but you can disperse the light for every single pixel that's in that picture. So you don't just get a monochromatic image, but rather you get a rainbow at every single location on the sky there. And that's really one of the most powerful instrumentation modes that any telescope, any observatory has, though it's usually over a fairly small field of view. So the MOS capabilities are over 5x5 arc minutes. So an arc minute is 60 arc seconds. So it's over quite large field of view. The integral field unit is much smaller. It's over a few arc seconds. So these instrument modes all complement one another. It's all about synergy. And so like a lot of times when we have targets of opportunity, we'll have people that will trigger and they'll say, hey, I want an image of this part of the sky. And so we say, okay, yeah, okay. So move the telescope there, take an image, and then we go about our business. So then we go, yeah, okay, let's go and do our thing. We're going to go do some speckles, blah, blah, blah. And then all of a sudden, an hour later, we hear from that same team and they say, hey guys, so listen, really nice picture. Thanks a lot. And we'd like to take a spectrum. And because we found what we were looking for and we want to know more information about it. And this happened a couple nights ago here on the north, actually during our last session, right? Which was like,
That's right. Sure did.
Yeah, so it happened right like 3 hours before our session. We took the picture, And then just as our session was getting started, we were taking a spectroscopy of a gamma ray burst. That was super exciting, and we found out from that PI a couple hours later that they found what they were looking for. Well, partially they found what they were looking for. So that was super exciting for us and the observatory and everyone. And then on the top right here, a bunch of weather measurements. So Lindsay and Roque are not actually observing from the summit. We don't observe from the summit either here in the Big Island. We are about 40 kilometers away from the telescope. I think Lindsay, you and Roque are about the same, something like 30, 40 kilometers away. Although the drive is
Yeah,
longer.
it's like an hour and 45-minute drive.
Yeah, yeah. So our drive is not as long, but we also have to do acclimation here. And I guess you guys don't have to do that. 'Cause you're at
No, we're at 2.5 kilometers, so it's not nearly as bad as yous.
Yeah. So we're at summit of Mauna Kea is about 4,000 meters. So the day crew always has to stop for about 30 minutes at least before they go up. So we need a ton of measurements of what's going on up at the summit, because we need one of Roque's jobs, the operator's jobs, is to look out for the telescope and the instruments. And so if there's any chance of humidity or dust interacting with the telescope or the instrumentation, we need to know about it. And so there's a bunch of kind of normal weather data here. And then there's a bunch of other sensors for the telescope that we're not showing here that we have to keep an eye on to make sure that the telescope is operating safely and effectively.
Okay,
I'm happy to pause here for questions or.
We're right on the same wavelength. I was just about to say, okay, we have a few questions. So I think this is just a 1 hour session. So we have about 5 minutes or so left.
Oh, that's it? Oh, I thought were we gonna go for 2 hours? Up to you, Jamika.
Oh, yeah. I mean, we definitely can. Am I remembering that
That
wrong?
way we get to see some speckles.
Yeah, no, we want to see speckles. Okay. All right. I just may have misremembered. Okay, perfect. So no rush. Sorry, whoever I just said we had. I was just texting back in the chat. Oh, we just have a few more minutes. So sorry about that. Wrong. We have a little bit more time. So we'll go to the questions now. So thank you for waiting and sorry about that. So can Gemini North and South work together on imaging an object? Of course, it'd be at different times, but can the two teams work together to get data for one particular science team? So they have a northern and southern hemisphere view. I see Zach nodding.
Yes. Yes, absolutely. So we do split programs a lot in the north and the south. So I would say, yeah, decent fraction of our programs are split with some amount of time distributed to the north, some amount of time distributed to the south. And so this is we have these large and long programs which go over multiple semesters. And a lot of times those are distributed both over the north and the south. Those aren't necessarily programs where they're like targets of opportunity, where something goes bang in the south or the north and we trade off. These are maybe more like sometimes they can be galaxy surveys, so that there's a big survey of galaxies. They want to see, the program team wants to see a set of galaxies that are only accessible or better accessible in the southern hemisphere, and then some sets of galaxies that are more accessible in the northern hemisphere. And so we split up those observations. But yeah, I would say about 20 or 25% of the programs have some component where it's the north and the south. And so targets of opportunity, like the one that's being observed right now, this is very common for program teams to split things up between the north and the south. So the program that we observed a little over 24 hours ago here in the north, They have time on the north and the south. And it makes sense because they don't know where these things are going to go off. And so they have telescopes that survey the entire sky every night or 12 hours. And something goes bang, they want to be able to see it. And we don't want to discriminate on whether it's in the north or south. And that's one of the amazing aspects of the Gemini Observatory. We're really good at getting on source on a target of interest very, very fast. We can move fast. Our computer systems are set up to let us know things really quickly. We have the 7-hour time difference, at least currently. So night and day are different in the two sites. And what can be seen geographically are different in the two sites. So it really makes for synergistic capabilities for these types of programs.
And following that, one of our regular participants has asked about spectra, because normally, well, with our Gemini North sessions, we're usually looking at some not actual images, but we're looking at some spectra that's coming in, but we haven't done that yet with this special target. Why not? Can you explain?
Yeah, just going back to the last question, I was remiss not to mention the Speckle team. So Zach, I mean, you guys have Zorro and Alopeke, and I mean, you guys have different blocks on different times of the year. Like, you don't have any more nights dedicated for the north, but you're in the middle of the run in the south. So maybe you can talk about like just why you guys have programs in both the north and the south. Why you have, I mean, you guys actually had to give the instruments to both the north and the south.
Because stars are everywhere. I mean, that's what it is, right? I mean, there's stars in the north and the south, and there's planets everywhere.
Right. So you guys are doing a survey, and like you want to like a lot of stuff you're sourcing from space telescopes that don't really care the north or the south, right?
Right.
'Cause there is no north or south. And so it's just you want to be able to have full sky coverage to be able to see all of anything, not discriminating based on hemisphere.
Yeah.
Okay, so I was just responding to that last question there. These rapid targets of opportunity, and actually everything that you all do, those the data are always proprietary for a certain amount of time. But for these RTOs, maybe that's a even more of a special case. So while with sometimes in our regular sessions we can see the spectra, we're not looking at any other identifying data from the target or anything, but we can see the spectra for these special RTOs. We're not able to look at that right now either, because this is such a unique case.
Let me so we can look just generally. So let me share this screen. So this screen is the kind of quick look tool of the observatory. And this gives a single frame that was just taken. It is shown down on the right here in this image display. And this is a GMOS long slit spectrum. So this was taken on the target that Lindsay and Roque are observing right now. And this is one frame of many. So each observation is probably something like 20 minutes or so. So they'll integrate for 20 minutes. So basically open the shutter for 20 minutes for GMOS, and then they'll close it, read it out, they see what they see, and then they do it again. And the reason why you want to do it multiple times is these streaks that run across the, well, this is one of the reasons, these streaks that run across the image here. These are cosmic rays, high energy particles, and they mess with the image. So these come from outer space, but it's not necessarily the signal that you want. And so when you build up multiple of these images, you can actually clip out this noise coming from these high energy particles. And so what you're seeing is a spectrum. It doesn't look like a rainbow, but it is. And the wavelength direction, so the rainbow direction is horizontal here. And then the spatial direction is vertical. And so the lines that you're seeing, these vertical lines there, these are also relics from the atmosphere. These are what's called air glow lines or sky lines. And these are from species in the atmosphere, usually molecules in the atmosphere that get excited and emit light. And so you see these all the time. This is another reason why the atmosphere is, I mean, it's great for a lot of reasons, like to live as a human, but for astronomical observing, it can be difficult to deal with. And so by taking multiple images and by moving the telescope so that the astronomical source appears in different locations, you can actually median out all of the observations, and you can get just a measurement of the skylines themselves. You can use that to create a model. You can remove those to some level. So you can remove all these artifacts, and then at the very, very end, you're left with just the astronomical source. And so every once in a while, as data comes in, you'll see a different frame that looks a little bit different. You can see as you move in the horizontal direction, there's what these like vertical striping kind of. This is different amplifiers, different detectors. So we have 3 different detectors on Gemini South, and then each one of those has different amplifiers. And so they have different properties. They respond to light in different ways. And so Lindsay, as part of the normal nighttime calibrations, will take what's called a flat field. It's internal to our telescope. We have this system called GCal, or Gemini Calibration Environment, which is actually where Zorro and Alopeke sit. So we can turn on different lamps and basically illuminate with a known illumination pattern this whole array, and then we can divide this out. The response function is what's called, and then you can remove these like vertical banding structures. So there's all these different types of calibrations that we can take, all these tricks that we do to try to remove the terrestrial aspect or the instrumentation aspect or the telescope aspect, remove all of that stuff and just get to the pure scientific glory of the object. And so what you see in this individual data frame may not look impressive, like where is even the source, what I can't tell, but they're spending an hour and a half on this source, which we have an 8.1 meter telescope. We have 2. I mean, this is a big light bucket, and we are dispersing out the light, so it's not an image where you're just dumping all the light into one bucket. Basically, you're dispersing this out into 8,192 pixels along the dispersion dimension, or something like that. And so you're breaking up the light a little bit. But still, it's a huge light bucket, so we should be able to see something if it were a bright object. And by bright, I mean like 10,000 times fainter than what the human eye can see. So if it were that bright, we'd be able to see it. And so that's what we call bright. Well, that's what I call bright. I don't know about the bright. Zach has a different calibrator. So that means it's a pretty faint object, and they have to build up signal over time. And so taking many of these frames together, calibrating them properly, really trying to understand the noise properties of the detector, and model that, and remove any spurious signal from terrestrial sources or from extraterrestrial sources that are not the signal of the object. That's incredibly important. We have, in fact, an entire team of people called the Science User Support Department that support users after they get the data. So from the time they get the data, then how do they remove all of these effects? So we take the observations, we make sure that the associated calibrations are done well in a way that allows them to do this. And then they users, so people that propose for observations, they use the software packages that the Science User Support Department develops to remove all of these terrestrial effects or all these instrumentation effects or all these telescope effects. So Lindsay and Roque are taking data right now. We are getting spectra, and this is the fruit of all of this labor, is this blank G-MOS image.
But you explained to us the importance of what we're seeing, and it's not really super blank. There's lots of information that can be gleaned from it, and you also touched on the importance of the wide variety of roles within the observatory that enable this amazing science. So you were just talking about the user support teams and how they work with the PIs of of these programs to help them with, among other things, sorting out the artifacts that are here that they don't want to have. And you have specific software that's used for data analysis. And so is all of that done in-house, the development of the software and any of the tools that your user community might need?
Yeah, so there's public software available. So, for example, my wife develops a public software which is used to we call it reduce. That's the verb. So, like, to remove all these artifacts is called reduce. So you're basically distillation of the data, removing all of the chaff from the wheat of the which is the astronomical signal. And so there's these publicly developed codes, and then there's these in-house developed codes. And so they work together. They're synergistic. And the publicly developed codes, they don't necessarily work with the observatories. They sometimes can. So, for example, the program that my wife develops, they work with the Keck Observatory primarily. And so they work with the instrumentation teams there, with the instrument scientists, and they try to understand better the instrument properties so that they can do a better job producing data to get the astronomical signal out. The in-house stuff that's done here at Gemini North and South, those teams specifically work on Gemini data, so they can take a little bit closer look at Gemini data, the parameters of our instruments, of the telescope. And one of the ideas, and this is something that's really going to be important for the future, is to have reduced data readily available for people to download off of our archive. So the Gemini telescope has this archive. And so this is an archive that I can use. So I can South 2024 E222. So this is a program that I helped to run on Gemini South. And this is the program designator here. And so what I can do for all of my data, so like 20 seconds after the data is taken, I can go on this archive and I can say, oh, I'm really interested in this frame, and I can preview it. There's the acquisition image. I can download it if I want. I can look at all the wonderful information that's here. Some of this comes directly from the screen that we were looking at before, this TSD. So it's really encoded in the data file itself. So I have all of that information in case I want to say, oh, well, what was the, I don't know, what was the thickness of the clouds when this observation was taken, or what was the seeing measurement when this observation was taken, or where was the telescope pointed, or how strong was the wind, or whatever. And this can all help me determine which data to use, how to use it, so on and so forth. But there isn't a tab here that says, give me reduced data. You can see there's a little space here available. And the point is, in the future, that this space here will be filled with, do you want to download reduced data? And so the Keck archive right now is called KOA. They have this capability for some of their instruments, a few of their instruments. You can actually take reduced data by the software package called Pipeit and and download it yourself. And it's a little bit kludgy. Sometimes it works, sometimes it doesn't. It's really tough to like associate calibration frames automatically. So sometimes human intervention is needed. But this, if you can reduce, you can see this image here. Clearly, there's vertical banding. There's the same thing that we saw here in the previous image. There's this little funny thing, which is our on-instrument wavefront sensor. So there's all sorts of artifacts. So you might see that image like, I don't really want to deal with like all the crud that's in there. So maybe I don't want to do science with that. But if you have already reduced data, then you can just pull that down and say, okay, I can do science with it. It's ready for me to analyze. And there's so much wonderful data out there. There's so much data that we have in the 20-year history, 20+ year history of Gemini, of both Geminis. And so one of the main goals of the observatory and many observatories now is to provide ready-made data so that anybody from the public can access it and start playing with it, analyze it, and discover something new. Because a lot of times when I propose for a set of observations, I'm looking for very particular things. I'm looking for that what's happening in this one galaxy, or if I take an image like this, I'm like, yeah, okay, there's these 3 things that I care about. What about the other 10,000 things in that image? Did anybody ever look at those? Maybe, maybe not. And so there's a lot of data out there where astronomers are singularly focused. It's tough. They have one question, and even trying to answer that one question is really, really tough. And so you have to put blinders on and say, well, I'm not going to pay attention to all this other stuff. But there's tons of archival data out there that have, that could answer many, many questions that we just haven't taken a look at.
So it's having this kind of data is, having it readily available is certainly going to be huge for especially undergrad, grad students, anyone, as you said, from the public who may want to interact with this data. But I believe some of the newer, like JWST, kind of has this available. They get data, and some portions of it is available soon-ish afterwards, that can be accessed by the public. Is that kind of what you're talking about here?
Yeah, that's right. So Space Telescope Science Institute also has a group of people that work on data reduction, and the same type of principle applies. I am the principal investigator for a Hubble program that's happening right now. In fact, we just got our last data a couple of weeks back. And so we can actually go and download severely reduced data from the archive. However, there's a lot of post-processing that still needs to be done. And if you care about, like, for example, the noise properties of the data, or you're really trying to look in the what we call low signal to noise regime. So you're looking at basically faint sources for the image, or the spectrum that you're taking. That reduction may not be good enough. And in fact, like, one of the things that my wife helped develop is, and she got money from the JWST fund, to develop a package that would increase the reliability of the noise property measurements of the JWST pipe. So this reduction pipeline spits out something, and it has still some issues with the noise, the way the noise is measured. And so this can be really problematic if you're trying to measure really faint things, because it can cause the noise to basically mimic signal and say, aha, there's that thing that I was looking for. But in fact, it's just a confluence of noise. And so that's a game that we play all the time in astrophysics, is like just picking out signal from noise. And if you get the wrong idea because you don't really know the noise properties really well, that can be problematic. So yes, Jamika, absolutely. Those reduction packages work, and they work spectacularly well for brighter objects or certain types of science. But if you want to push them further, sometimes they can work, sometimes not. So you need to be cognizant of what all goes into it. And personally, as somebody who goes from like proposing for the observations to taking the observations to reducing those observations to analyzing those observations, I always want to know each stage of that process because they feed back on one another. And the scientific questions that you can answer are sometimes dictated by your ability to reduce the data in a way that's sufficient for that particular scientific question. If you're grabbing data from an archival data reduction process, you want to make sure that that's reliable to different levels. And so there's usually disclaimers associated with this when if you read the documentation associated with the automated reduction, say beware of this and this and this. If you want to do it in this way, make sure that you check this and such and such. And the Dragons team, which is the software that's being developed here at Gemini, they're very good at this to have like really good documentation about, well, here's what it generally does, but if you're moving into this edge case where you really want to know something about such and such noise, or this artifact here, or you're looking at something over here, and we're confident about the reduction here, but maybe not in this part of the data, then beware and maybe do some extra things.
That's really good to know, especially for anyone who may want to even just kind of look at what actual astronomical data looks like before and after it's been fully reduced. Because when we have people who join our sessions for the first time, they're expecting to see, potentially some very colorful images, amazing things that just pop out that they've seen in magazines or on TV and documentaries, and they're like, but why doesn't it look that way? And so I really appreciate that you all always talk about what the difference between the science data and then how we go from that to something amazing that we may see in a documentary or in one of the beautiful astronomical calendars that I have hanging up in my room right now from NASA, for example.
Yeah, and actually we just got so another way that you can get time on the telescope is to ask the director directly. So this is called director's discretionary time. Every telescope has it. And it's actually a group of scientists here that are the arbiters of these ideas. So you send in a formal proposal and you say, hey, this is something I'm interested in. And one program that just came in is to basically take legacy images for the Gemini telescope. Some of the things that we have in this room, like I guess if I'm on the main conference room camera, this thing over here, this all these images are taken, or the one right behind Jamaica, these are taken with the Gemini telescopes. And so
Just finishing up the rapid duo here. If you want
and
me to
so
go
so this
you
is
ready for
a
it?
program
Yeah.
to take new images, but what we see is black and white image, and we don't really necessarily understand initially what that looks like. It's going to look pretty cruddy, but then through this removal process and through understanding the properties of the data, understanding which wavelength of light it was taken in, what that corresponds to in terms of what the human eye would see, then you can make these really beautiful pictures. I actually have to run over to our control room for a second. I'll be right back.
Sounds good. So Zach, when it comes to reducing or just interacting with the data, Speckle data, how different is that than from dealing with this kind of data? For example, I imagine that it's not quite the same.
No, it's not. For the Speckle data, there's a specific reduction pipeline that the team uses to reduce the data. And it's their own pipeline. It was along with a whole bunch of others who have helped it and wrote a lot of it on the way. And so, but it's not a pipeline that someone who has no knowledge of Speckle could pick up and run it. And it's a very specialized pipeline. So for example, Gemini has, GMOS where you can take images, and there is a reduction pipeline for that called Dragons, but as well, there are other pipelines that could be adapted to use that. For Speckle, that's not really the case. So it's a very very specialized pipeline.
For the speckle imaging for your data, eventually I imagine it is made public after a certain amount of time. So we were just looking at the Gemini archive. Is there an archive where we can find images that you and your colleagues on the NASA Speckle team keep your data?
Yeah, so for the NASA Speckle team, you can go, there is a website called ExoFOP, and it stands for the Exoplanet Follow-Up Program. And on there, if a star has, and they may just, and to be honest, they may put all their reduced images there. If it's for because the thing with the other nice thing about Alopeke and Zorro data at Gemini is, unlike all the other data, well, with the exception of Maroon X, and I guess Ghost, although I don't know whether Vinny's still reducing the data. For the most part, if you're using GMOS, GNears, any of our normal facility instruments, you have to reduce the data. You have to go through, you have to run Dragons or Gemini IRAF on, or whatever data reduction pipeline you want to use on it. For the Speckle data, the team will reduce it for you, so you just basically get back the reduced images. The basically what I showed earlier at the end is what you get. And so if you go to ExoFOP, you'll see those results there basically. The raw data is available on the Gemini archive, but the reduced data is on ExoFOP.
So I've just dropped a link there in the chat for everyone to check out the ExoFOP. They're under outreach. There's the science visualization and illustration, and it talks a little bit about things, but then there are some really amazing images that are there. But I'm trying to find the regular data. Could you?
Yeah,
I'm
so
looking
on that page, there's a in the middle of the page, there's a link that says Exoplanet Follow-Up Observing
Yes,
Program homepage, and you go there, and that spits you to their database.
got it.
Um,
Okay. Ooh, okay. Oh, this is incredible. Let me put this, let me drop this. Oh, Brian is back. Sorry. Okay. So we can check this out and maybe do a little tour a bit later if we can. But thank you for this, Zach, because it again really showing the differences between data from a ground-based observatory and then this kind of data is just pretty incredible. And this is welcome. Okay, sorry, I'm just going through looking at things now. Brian, can we get a quick check-in with Roque and Lindsay and see what's going on with our RTOO?
Yeah, so I think they're actually pretty close to done. Zach, you guys are up pretty soon. So I took a quick look at the sequence that's being taken, and it looks like it's maybe one more step and then close to done.
Oh.
Yes, we have one more step. So we have about 40 seconds left in the second to last observation. And the Zorro team is already connected in the control room, and we have.
Oh,
one
awesome.
extra.
Oh, okay.
Oh, great.
Cool. So we're gonna do the transition then. Yeah, this is one of the awesome things about the observatory is that yeah, on a given night, I mean, using all these different instruments. And most observatories they use one, maybe two instruments at most. But it's just switching between instruments all the time. So that and it's gonna be a quick switch. This is our tertiary mirror. It just moves. And in fact, you probably end the sequence in the decal environment that just put in the pickoff for Zorro and away you go.
It's already there. If you can share your screen, you will see like a little mirror that will put the light to Zorro when ready.
Wait, do you have GCal stuff at the
That's-
end of the RTO?
We already have our calibrations.
Okay. So you took the calibrations prior to the last two steps of the science sequence.
Exactly, yes. We did
Yeah.
a bit of science, then calibrations, and then a little bit of science.
Perfect. Yes, that's even more efficient. So yeah, Zach, you want to talk about what that green thing is next to the science fold?
Yeah, so basically so Alopeke and Zorro used to be basically, well, actually Alopeke and Zorro never did, but Dizzy, which is the previous iteration of Alopeke and Zorro, basically they put it on to the bottom of the instrument cube. So where on the diagram it says GSAOI, they would put another, well, actually I think it was on the side because I only did this once. I think actually F2 got taken off, and well, maybe not F2. I can't remember which one got taken off. Anyways, you put this visitor instrument on the side, and it was an instrument change. You would go up there, they'd have to take an instrument off, you would have to put an instrument on, and then at the end of the run, you would have to go back up there, take the instrument off, pack it up, send it back to the US, or yeah, basically back to the US, because Dizzy went to like 20 different telescopes at a time over the course of a year. Um, and what they did instead was GCal is the Gemini calibration unit, and there was enough of a space where you could put basically this miniaturized Dizzy. And Dizzy was I don't know, it was a box that was maybe 2 to 3 feet by 2 to 3 feet or something like that. And so but there was a lot of empty space in it because they had light path. It's all about the light pathing. And so what they did was they went in and they made a condensed version of it that could fit into GCal so that they didn't have to go up to the telescope and put it on. And they don't, and that means the observers don't have to the uh go to the sites. So for example, we just heard that the Zorro observer is on. I believe it's Sarah. I think it's Sarah who's on tonight. And so they can observe from the US instead of having to fly to Chile and have to install everything, which is great on the one hand that you don't have to go anywhere, but it also stinks because going to Chile is fun. And observing at the telescope is fun. So it's balancing what's costs and stuff like that. But so the way though that they get the light for Alopeke and Zorro is there's this little tiny mirror that they basically put on a conveyor belt. And so when we want the light to go to Alopeke and Zorro, it rolls out and blocks the light that it is put in the light path from GCal into the rest of the instrument or rest of the telescope. And so eventually what will happen is when we switch over to Zorro, you'll see the mirror in the middle of that diagram there rotate so that the light now goes to GCal, and then the light will be put into Zorro. So it was a fun bit of engineering, is what I've heard.
How big is it now?
Oh, I can't remember. I think it's like It's like a foot by 2 feet or something like that.
Yeah, yeah. I think I've seen them in something.
I mean, we had it in the lab at North for a little bit because we were putting the H alpha filter in, and I can't remember
Right, I
how
remember
long
that, yeah.
that was.
Nice. So I think you probably switch in what, like 5 minutes, something like that.
You went out.
What's that?
We didn't
You
hear
cut
it.
out.
Oh, sorry. I think the switch is going to happen in like 5 minutes. And so what is going on with the NASA Speckle team right now is like the switch is impending.
Well, so I don't know. Can we actually pick up Sarah on the Zoom?
Let me try moving this closer to where that is. Sarah, are you there?
Yeah, I'm here.
So I have the Meet the Scientist call here. If you talk, can people hear you? Can you?
We were
Hello,
able to
can
do
anyone
that.
hear me?
Yeah.
Yes. Hi,
Yeah.
Sarah.
Hello.
It's picking it up. Do you want to tell people how we're getting ready now? It's about, let me see. 10 minutes until we switch. There's 539 seconds left in readout.
Yeah. So we were just wondering, Sarah, about your general process.
Yeah, I just set up the software, honestly. Click some buttons, type in some passwords. I set the parameters to the kind of things that we need for the camera. So our exposure time is 60 milliseconds and stuff like that. I'm also looking at our observation list and picking targets that would go well with like different parts of the sky. So if we want to stay in one part of the sky, I'll find a bunch of targets in that area that are good for tonight, or, try to find the best things and then pass it on to Lindsay so that she can put it in the queue. Other than that, I'm just kind of hanging out and waiting until we're ready to go.
So how many targets do you guys have for tonight? A lot.
However many we can get done. They're usually, 7 to 9 minutes each, so we can rapid fire them. I think on average, it can be anywhere from 20 to 30 targets per night.
The first night we did just over 50, I know.
Oh, 50.
Yeah. And last
Wow.
night we were more like, I think it was just shy of 40, I think, last night, because we had that fault at the end of the night.
But you guys have
Okay.
had also
Well-
really excellent conditions, right?
Yeah, we've been CT 50, IT 70. Rocky's just really fast at the sloughs.
That's true. He is. He's
Yeah.
right on it.
Yeah, I mean, in terms of total targets available, I mean, I think the two largest programs in the OT or in Gemini systems are Steve's and mine. So I think there's at least over 800 targets in those two programs.
And then we have other programs that have a single target, like Brunex transits that are 9 hours, that are just a single target. So our night logs can look very, very different from night to night. But if you're an operator on a Zorro or Alopeke night, you're getting your pay in.
Zach and Sarah, could you maybe explain a little bit about the role that different team members play on the Speckle team?
Sarah, you want to go?
Yeah, sure. I'm fairly new. I started about 6 months ago, but I do observing runs, so I'm one of two generally that take the data. And then I've also been training on how to reduce it. So I'm all involved in the data at the beginning. And then I send out that data to the PIs. That's my role so far. But I'll probably start looking into science stuff a little bit later.
And Zach, so and how does your role on the team compare with Sarah's? Because how long have you been on the team, Zach?
Officially or unofficially? Officially, it's been what, 4 months?
Officially. Okay.
Yeah, officially. I mean, I've been on the periphery of the Speckle team for at least 6 years or something like that. So,
Oh.
um, but I mean, for my position, it's more of uh, a science position. So I have research projects that I'm doing with Alopeke and Zorro. Uh, I help out as needed on observing runs. But but we have two observers, Sarah and Colin, and they're both great. And so for the most part, they handle the observing, and then if there's ever a need for someone else to step in, I come in and do that. Uh, but yeah, a lot of what I'm doing is more science related, uh, and with my own projects and that kind of stuff.
So in terms of the types of objects that you're looking at, does that really vary widely, or are they more or less the same?
Primarily, all of the targets are stars, but there are, I mean, the overwhelmingly vast majority are stars. But there are definitely, we've had uh, people looking at quasars, and extragalactic objects. I've been part of a project for that. We've had people who look at asteroids, and try to resolve them and see if they can pick out their shapes. We've had people look at stellar occultations, because one of the things that is nice about Alopeke and Zorro is it's not just a speckle imager, it's also a rapid imager. So we can put it into a wide field mode, um, where it basically has a arc minute, so 60 arc second field of view, and the ability to go take rapid exposures, which is different from GMOS, for example. So when GMOS takes an image, it takes about 30 seconds uh, for it to read out. So for that data to be saved. And for Alopeke and Zorro, it takes about non-existent time, like milliseconds.
See that in a
So
second, by the way, Zach. So I just put up our sequence executioner. This is the thing that counts off what we're observing. And in 118 seconds, GMOS will attempt to read out, and we'll watch how long that takes.
yeah, and so by allowing to go that fast, you can look at other things. So we have people who look at pulsars and their timing. We have people who've looked at GRBs, and X-ray binaries and timing those and combining them with radio observations. So the overwhelming majority are stars and stellar, specifically focused on supporting exoplanet missions. But there is a large subset of astronomy where Alpec and Zorro can be useful.
So thank you, Zach. I was very surprised to hear that sometimes the target for Zorro or Alopeke are actually asteroids. Wouldn't that seems like an unlikely target? But you said to characterize the shape of the asteroids. Are these ones that we would find in the asteroid belt, or these more like Trojans around Jupiter or Neptune?
A lot. So I think there's been Ceres. Ceres has been imaged, I think.
Oh,
We've definitely done, I mean, not speaking of asteroids, but dwarf planets. We've done Pluto. We've done some of the moons of Neptune. We did a stellar occultation of Neptune as well. We've done a lot of work with near Earth asteroids. So that's been a wide field. And so yeah, as we just to look at this, now GMOS is reading out. So in about 30 seconds will be when that ends. And so while for anything, basically anything longer than 30 seconds, like in terms of exposure time, GMOS is the way to go. But if you want to go faster, that's when Alopeke and Zorro come in. So
Okay,
yeah,
Speckle time.
Speckle time.
Speckle
Speckle
time.
time. We're slewing, Sarah.
Great, thank you. I'll turn the video on.
Let me see if I can bring up the. There we go. Okay,
I'm
cool.
highlighting
Okay,
two.
so I'll share Rope's screen.
Is it possible to put it in between this first one and the next one?
Yes.
Thank you.
So between Q312 and Q130?
Yeah.
Okay, sure.
Zach, just feel free to jump in anytime, explain what's going on, but also we can just watch the speckles.
Yeah, so this is the Zorro control screen. Yeah, so the two cameras on. So another good thing about Alopeke and Zorro is you get two shots with one go. So there are two cameras that are taking a red and a blue. And for these two, they're focused, or the filters in them are narrowband filters right now, between 562 and 832. Well, between 562 is the blue filter, centered at 562 nanometers, and the red is centered at 832, and they're both 40 nanometer filters, so they're very narrow. So
That is actually like kind of, well, yellow and really red for humans.
yeah, I was trying to think of what the equivalent was.
532 would be, yeah, yellowish, and 8 would be past the range of human seeing, but at the red end.
Yeah. What was the thing here? Where was?
So the telescope's actually moving right now, right? So
Yeah, so at the moment, Rocky isn't sending light to the instrument. He's sending light to the acquisition camera.
Yeah.
So that he can find the guide star, because that was a log slew. So it doesn't tend to show up right where you want it. So he'll find the camera or find the guide star and then send light to the instrument and start the guiding. After that, we usually have a lot of very short slews, and so it's much quicker. The guide star just kind of shows up where you want it, and it's very quick and easy.
yeah, awesome. Thanks for that explanation. Yeah, and I think I got on the TSD quick enough that we actually saw, so the telescope was in place, the circle wasn't moving, but the dome structure was. And this is pretty common actually, like the telescope moves and then dome kind of catches up. And so the dome was just doing its last rotation, so that black area lined up with the telescope. So there was no vignetting of the field. And then once that happens, then okay, we'll find the guide star. And then once everything's guiding, so telescope's tracking, and there's also these fine movements that are keeping the telescope precise spot that it needs to be at all times. Then light is sent to the instrument, and then the acquisition can occur. So we can go back to the Zorro screen.
Sorry, just change the game.
Yeah, the focus is moving along.
Okay, that's probably why it looks weird.
So this is when all the exciting stuff is happening. This is when the this is the activity of the night, and then it's usually better when it's boring because that means you're taking data and photons are coming in and everything. This you want to do it as quick as possible, but also carefully. And so this requires Lindsay to keep an eye out for things, Sarah to keep an eye out for things, and okay to keep an eye out for things and do work. So everybody has to work in tandem and make quick decisions and check that things are in the correct place. And yeah, keep in mind they're going to do like, well, tonight they'll probably do like 20 to 30 of these as well. So it's a not hectic night on Alopeke.
Depends on the magnitudes of the targets.
So Zach, as we're getting set up, like what should we expect to see once light is sent to the instrument?
Well, I mean, you'll be able to see the speckles, and that's about it. So you'll see the speckles from the star, and you'll also be able to potentially, based on the shape, see if there's a companion. But you know,
I'm not sure. No, I don't think I've ever seen that.
Just to be clear, this is breaking. So this is the same image basically. So the left and the right will be the same, looking at the same star, right?
They'll be mirrored.
But it's there's a dichroic in place, right? Here we go. So dichroic in place to break up that light, whether that's the filter or whatever. But somehow we're looking at different light on the right than on the left, but it's the same source.
Yes. Yeah, there's a dichroic. I think it's at like, I think it's 650. No, it's not 650. Maybe 690 something.
Yeah.
So
the redder light is on the red GUI there, and the bluer light is on. And by the way, you guys have one of the coolest GUI. This is like one of the first observations that I saw with Gemini, and I was stoked. I was like, oh, you can actually see something, and there's colors and stuff.
yes, that it is the nice thing about Speckle is that you can actually see what's going on in your images as you're taking them. I mean, it helps that the images are 60 milliseconds. So, you know, that definitely is a huge help, but you know, it's nice.
And so can you give us an idea of what Lindsay is doing right now?
Well, this is Sarah doing this. Lindsay is...
okay.
Lindsay doesn't have to do anything for this.
I'm just keeping the night log and putting things in the queue, basically. Sarah's doing the hard work and Rocky is doing the hard work.
But so what Sarah's doing is basically centering the star in our data or in our frames and setting it up so that you're not taking the whole field of view because you don't really need it. You just need this little part where the star is. Then you set how many data cubes you think you need, the number of sequences for the target, depending on its magnitude, which isn't shown here, but we have it in a spreadsheet. And then observing. So you can see on the bottom there, you can see the top status bar is kind of how many data sets have been taken in a cube. And then the bottom one is how many cubes you have to go. So we'll be here for 7-ish minutes and watching the speckles go by. You kind of get some information about photon counts from the running tabs below the two windows, but for the most part,
Is it the text that's being output there?
yeah, but for the most part, it's not that. It correlates to how many. I mean, if you're saturating, then yes, it's great. But other than that, there's not a lot of info in having 2,000 counts. So yeah, we just go around doing this all night.
So what do you suppose the scientific question of like a program like this is?
Well, I think I know this program, and I think this is exoplanets.
Okay.
So,
Ooh, exoplanets.
This is most
Planets
likely
outside the solar system. That's crazy. That's
this is
crazy
most,
talk.
this is most likely a star that someone has either found an exoplanet around or suspects an exoplanet, and we are following up on it to see if there is a companion star nearby that may affect any parameters of said planet.
So you wouldn't expect to see a planet in these observations, but you might see a companion star.
No, the contrast between a star and the planet is too great for us to see. That's what HWO is going to try to do, hopefully, in, 15, 20 years. Uh,
The habitable
yeah,
worlds.
Habitable Worlds Observatory. Um, and so hopefully we'll be able to see that contrast limit.
And so if there were multiple stars in the system, like what would the scientific question be? Like, does having two stars affect planetary formation or something like that?
Well, the scientific question would be, if you have two stars in the system, then the light that you get from the light curve, because these are all test targets, is now diluted because you have two stars there. So you need to figure out one, which star the exoplanet is orbiting around, and number two, how much light is being contributed by each star in order to determine the stellar properties, which then can go into planet models and figuring out all that stuff. But then there's also just the fun scientific question of binaries are fun. So learning more about them is always great.
If this were binary stars, what would we see here? I know the stars wouldn't be, of course, they wouldn't be very close. Would we be able to see them potentially in the same field of view? And if so, what would it look like? Because this one star here, I mean, it's incredible what we're seeing here. If I didn't know it was one star, I certainly could imagine that it was more.
Yeah, so it depends on the magnitude of the other companion, like how bright it is compared to the other star, and what that separation is. If they are right on top of each other, then we wouldn't see anything. But if they were separated, then you could see possibly both of them resolved as two speckles, and sometimes that does happen. Or you would kind of see it as a donut. Well, not as a donut, but as an eclair, as this elongated shape. And this one kind of looks single, but you never know. Maybe the data reduction will pick something out. Over the course of the night, we do look at known binary stars so that we can calibrate the data. But it's always interesting to see what the reduction pulls out. So yeah, we're almost done.
You won't actually know until you reduce the data because I mean,
Yeah.
as you said, in some cases you can actually see two stars when you pull it in. I remember Colin saying like, "Oh, that's a binary. Okay, we're actually going to switch targets to something else." But in this case, you won't know until the data are actually reduced.
Right. And we don't reduce it on the fly, so this won't be for a little bit.
Are the so this is a target for a specific science team. Are they able to eavesdrop like we're doing here with Gemini South team? Are they able to do that when you all are taking their observations?
This particular program, so as it is in band 3, the eavesdropping that we normally offer for band 1 and band 2 PIs does not extend to band 3. So they would not be able to. The other thing is that I don't know whether you would for a speckle night, because it's not like we're going to stay on this target for long. We are on it for 7 minutes and then we are gone. And so, you know, if you have, you know, a 9-hour Maroon X observation, then it may make sense. But, you know, technically you probably don't, unless you just want to watch the speckle night, which sure. But for a speckle night, you're jumping around to so many different programs, so many different targets that it doesn't really make sense. So
Yeah, that's right. You're right. I kind of was thinking that maybe there were 1, 2, or 3 targets for one program together, but no, that's not the case.
yeah, I mean, it really
that does happen
depends.
on a speckle night, right, Zach? Like you do have multiple targets from a given program.
Right.
That observed, and so potentially as a PI you could come on, and even for band 3 PIs, I mean, sometimes we make exceptions if people are really interested to come on. So it's all at the discretion of the observer and operator, of course, but the people can come on and watch if they would like to watch. And I
Right.
will say, in addition to a 9-hour Maroon X transit, you could also watch like a 2-hour observation of a proto supercluster at high redshift, just for an
Yeah.
example. So pulling an example out of my head.
This sounds
But-
oddly
but, you know,
specific, Brian.
I mean, I'm an oddly specific kind of guy.
I don't know whether anybody wants to get woken up at 3 a.m. and told, hey, we're observing your target for 7 minutes. Hop online and watch it.
Rope called me at 3 in the afternoon. I was fine.
It was also a 2-hour observation.
Very different. So so there are 30, 40 targets that'll y'all be looking at for the rest of the night, Lindsay. And so you and Sarah will be and Roque will be working together to get through all of those targets. And once that happens, what's that next step, Sarah, as far as your role? Oh, I don't know if she heard me. Sorry.
Let me put you.
Thank you, Lindsay.
Go ahead,
I
Sarah.
think I kind of heard all that. Can you say that one more time?
Absolutely, absolutely. So once you finish, you and Roque and Lindsay, once you finish going through your targets for tonight, what's the next step in your role that you'll be doing with this data or in support of these programs?
Right. So someone else sends the data to a server that I have access to. And I take that data and I run it through this really long pipeline to get it ready for the PIs. So it kind of turns it into plots and like easy to read data files. And yeah, I just send it to them. That's the end of my role there.
Well, Sarah, we're so thankful that we were able to actually interact with you through Lindsay and Roque's. Thank you. They're set up there at Gemini South. I am so thrilled that we had this opportunity to connect and shadow Roque and Lindsay through working with the NASA Speckle team. Zach, thank you so much for enabling all of this, and Brian for the coordination, because this was so special to have this amazing group of experts for our very first Gemini South session.
Yeah, I want to echo everything you said, Jimmy, because this has been really wonderful. Really appreciate the Gemini South crew letting us shadow you guys for the first time. And Zach for joining, Emily for joining. It's just amazing, like all the different VNC connections that we have. Everybody's geographically dispersed, and yet we all come together here for this same purpose and to just be super excited about what's up in the sky. So love it, love it, love it.
And hopefully we'll have more of it. Oh, quick question, last question. About this is a question about the live image display. Are the Speckle images really saturated that much, or is it just the the SAO image setting?
Yeah, it's just the scaling.
Yeah.
It takes a while for it to scale.
Target.
So there's an auto scale feature, is that right, Zach? Like where there's
Mhm.
some running in the background that's outputting that's checking the pixel distribution and then scaling.
Yeah,